cetera, et cetera. So we converge to zero error mathematically. However, that's a mathematical proof, and you have to connect up these things with the real world. Now, we can simulate what happens, and on that particular robot, we did exactly what I described. And the error improved by a substantial amount. It was probably approaching a factor of 100. But then the error started getting worse. And I say, well, I've got a mathematical proof that it's going to converge to zero. And so then we say, well, can't I keep iterating? When I get to 15 iterations, the robot's making a whole lot of noise. And well, I didn't want Janan to get angry that the robot was ruined. The doctoral student who was running the experiments didn't want to ruin it before he had finished his thesis. So we didn't continue. We went to simulations. So now we start simulating this law that has a mathematical proof that we get zero error if you run it long enough. And the simulation says no. It goes to exponential overflow on the computer, the error. But I have a mathematical proof that it converges to zero. So we shorten the trajectory and take longer time steps. And turns out mathematical proof is right. The error goes, after we did this modifying the problem, the error went to 10 to the 51st radians. That's a lot of radians in a 6-second trajectory. 10 to the 51st radians error, and then at iteration 10 to the 5th, the error is essentially zero. The computation says 10 to the minus 48 radians. So all you have to do is be able to move the robot so fast that it gets to 10 to the 51st radians in 6 seconds. And then you can keep learning. And then after 10 to the 5th iterations, you get zero error. Okay, so the mathematical proof is correct, but it's useless in the world, and we have to be smarter in coming up with our control laws. But how to be smarter? Well, we need to, let's start out writing what the control law is before we're smarter. So this U is my input well, I'll put a +1 here. So this is the input at time step. Well, we'll do this. So this is discrete time now, because I have to store data. So at time step little k, an integer times cap T, my sample time. And this is run j plus 1. I'll write that as whatever the command was at the present time, plus some gain, which I could make 1, times the error in this run. So run number j at time step k, this is the command I put in, and this is the error I saw. We put in 1 step delay saying that whatever command I put in, I should expect it to not, I can't expect it to influence the error immediately. If I wrote a discrete version of this, xk plus 1 is axk plus buk, and yk is cxk. So if I change uk at time u at time k, that changes x at k plus 1, and that changes the output at k plus 1. So I should look at the error at k plus 1 when I compute the control action at k distance. So this is the one that is guaranteed to converge, but has horrible transients. In order to fix such a problem, we need to come in and put in some kind of compensator. So we make it okay, so now, what's the source of the trouble? One way to look at it is, we said if the robot link was 2 degrees too small, add 2 degrees to the command at a specific time step. So if that's fine if the error was a constant, let's say. But now suppose the error was a sine wave. Now, feedback control systems or differential equations, if I put in a sine wave here, I will get a sine wave coming out, same frequency, but the fact that this dy dt will put in some phase lag so that the sine wave coming out is a little behind the sine wave going in. If I have a first order differential equation, the maximum it can be behind is 90 degrees. But if it's a second order system, it can be 180 degrees. If it's a third order system, 270 degrees. So if I can, so in there is a possibility that there's some error at a certain frequency for which going through the differential equation of the real world puts in a phase lag of 180 degrees. So if now suppose the error was a sine wave at that frequency, then when I said the error was 2 degrees too low, at this point add 2 degrees to the command, do that for every time step. Then when it goes through the system at that frequency, it will get a 180 degree phase change, and that's the same as changing the sign, S-I-G-N. So now it's a minus sign, and that means I'm making the error bigger, not smaller. So some frequencies the error will be getting bigger. The reason things converged was the first time step converged as if it was the only time step involved, and after that, then the next time step looked like the first time step. So the convergence came in a wave starting at the beginning and progressing to the end. But while that convergence is happening, steady state parts with the sine waves can be blowing up with the phase lag. Okay, so in order to make a good design, we need to put in some sort of differential equation, well, difference equation, in place of that gain, which will put in phase lead at the frequencies for which there's too much phase lag, and then you can stabilize the learning process. And in the case of that robot, result in improving the tracking accuracy by a factor of 1,000. Now, this is learning control, and the learning control problem is, it says I want to do a specific maneuver and then I'll go back and do it again, starting from the same initial condition. There's a related field, instead of iterative learning control, a field called repetitive control that does the same concepts for a periodic command or trying to eliminate a periodic disturbance. Those two are very similar. If I'm trying to get rid of the effect of a periodic disturbance, I look back at the error one period ago and try to change my command. So one example that I've worked on is Thomas Jefferson National Accelerator Facility near Nassau, Langley. And that's a 8 giga electron volt accelerator, accelerating electrons. So it's for physicists. They accelerate the electrons along a straight stretch. It's like the running track for athletics. A straight section, then a curve, and a straight section and a curve, and you make the electrons go around essentially at the speed of light. But the acceleration is done by electromagnets, and so there's 60 hertz. Electromagnets, you need DC current, and AC current, the voltage is supplied as AC, so you have to rectify AC current to DC current, and there will be a little bit of 60 hertz in there, and that means that the magnets vary their strength at 60 hertz a little bit, and that means that the beam wiggles. So we can make a similar learning law that looks back one period of the 60 cycle supply voltage and learns to command the strength of the magnets to wiggle the opposite direction in order to cancel the effects and get better focus of the beam. Other applications, computer disk drives. Nowadays, nearly all computer disk drives use some form of this kind of learning on each track of the computer disk. The track, computer disk has tracks written on it, but the tracks are written while it's spinning. And it tries to be a circle, but because it's spinning, there's a little vibration, so there's some wiggles in the track. So if then the control system to follow the track has a certain amount of error, if you can learn to follow the track more accurately, then you can put the tracks closer together and put more storage on a disk. Other applications, well, we've done